In many design optimization methods, the resulting shape often contains complex internal structures. These structures create multiple isolated volumes inside the object, even for very simple loading configurations. They prevent easy removal of material encapsulated in them, and also disrupt the inner cavity that could be used for functional purposes. Shell structures provide a compelling alternative, where the object is interpreted as solid enclosed by two-manifold surfaces, creating a single connected cavity inside. We propose a new structural optimization approach for designing minimum weight shell objects. Our approach takes a 3D shape and produces a lightweight shell structure that withstands any of the prescribed force configurations. The main issue in shell design is that large thickness values may result in self-intersections. Our approach overcomes this challenge using a temperature field obtained by solving the steady-state heat conduction problem within the shape boundary, and uses that as a proxy for the varying shell thickness. The idea here is that the temperature field is the solution to the Laplace equation, and therefore the resulting offset surface is by design intersection-free. We obtain the temperature field inside the object by creating a temperature gradient between the boundary surface and the shape skeleton. Our system computes the resulting steady-state temperature field inside the object. The isosurface at a certain cutoff temperature forms the inner boundary of the shell. Higher boundary temperatures correspond to a thicker shell, while lower boundary temperatures result in thinner regions. Our optimizer adjusts the boundary temperature iteratively to manipulate the resulting shell structure. The optimized result is structurally sound under the prescribed force configurations. Our approach addresses classical structure design problems with fixed and known external forces, as well as problems including multiple external force cases. For multiple loading configurations, our algorithm evaluates the performance concurrently for each loading configuration. Our approach also covers a more general class of problems involving force location uncertainties. It creates a thicker shell around the parts where high stresses may develop under the given force location uncertainties. Notice the handles of the pitcher and mug models. Our method can be used for thickening open surface meshes to generate 3D printable solid shells. The optimized model can be 3D printed directly without further adjustments and withstands the prescribed force configurations. As our method creates a single connected void inside the object, internal supports or excess material can be removed through a single access hole. For SLS or polyjet printing, a water jet can be used to clean excess material, while for more complex models, a 3D printing technology which allows soluble support material can provide a more practical solution. In either case, only a single access hole is required. We designed a beam model for testing and validation of our algorithm. The beam is optimized to withstand 115 newtons of force under both tensile loading and 3-point bending configurations. For comparison, we show an identical weight, uniform thickness beam. In tensile tests, both models withstand larger loads than 115 newtons. However, in 3-point bending tests, the uniform model fails to satisfy the design constraint, while our optimized result can withstand 153 newtons of load. Our method balances tensile and bending performance by moving material toward the center. Thank you for watching.